Hello and welcome to this lecture on advanced electric drives. In the last lecture, we are discussing about the dynamics of torque production in a synchronous motor when it was operating under vector control. By vector control, we mean gamma is equal to 0 and IDS is equal to 0. So, just to recapitulate what we have done in the last lecture, we can just go back to our Phasor diagram. So, we have the d axis here and this is our q axis. And the field current is naturally along the d axis. So, we can say that this is the field current and this is our IF, and due to the field current we will also have a field induced EMF, and the field induced EMF is in the q axis. So, this would be our field induced EMF that we can call as EF, and the armature current phasor can be in any arbitrary direction. So, what we do here, we have this is the current phasor IS, the current of the stator, this is also a phasor, this is also a phasor, all these things are phasor quantities, and this angle is gamma. And this IDS, this IS can have two components, one along the d axis and the other along the q axis. So, we can say that this is the d axis component. So, we can call this to be IDS, and if we project this along the q axis, this will be the q axis component, we can call this to be IQS. So, we are talking about the vector control, and by vector control we mean IDS is equal to 0. So, for vector control of synchronous motor, we have IDS equal to 0, which also means gamma is equal to 0. And if gamma equal to 0, the torque equation becomes very simple. So, what we have here, this is the equation for the torque. We can see that this is the equation for the torque, Te is equal to 3 by 2 into P by 2 and the expression within the bracket. And here if we put IDS equal to 0, this quantity will vanish, this is 0, it is the product of IDS into IKD. This term is also equal to 0 because this is the product of IDS and IQS. So, what we obtain here is this term, which is LMD into IF plus IKD into IQS. And furthermore, if we keep IF constant, so for example, if we keep in this case IF constant, we do not change IF. If we keep IF constant and IDS is also equal to 0, there is no flux change in the d axis. IDS is non-existing and the field current is kept constant. So, in the d axis there is no flux change, and since we do not have any flux change in the d axis, the damper winding currents in the d axis will be 0. So, we can say here that IKD is equal to 0. So, if IKD is equal to 0, now see the torque expression. If we put IKD here equal to 0, the expression for the torque finally will be 3 by 2 into P by 2 into LMD into IF into IQS. So, it is something like a decimation. We can keep IF constant here. What we can do here is that IF is constant. So, we can replace it by capital IF, it is a constant quantity, and we can change the flux with good dynamics by changing IQS. So, this is the principle of vector control of synchronous motor. We keep IDS equal to 0, or in other words the angle gamma is equal to 0. So, the whole current is aligned along the q axis. So, this is a general phasor diagram, and for the vector control, the IS will be along the q axis. So, we can say that this is our new IS for vector control. So, the stator current or the armature current is aligned along the q axis, there is no component of current along the d axis, and the torque can be controlled with good transient response by controlling the stator current, that is Is, which is same as Iqs. Now, what we do here is that we make one relaxation. We have assumed that If is constant. Now, if we say If is variable, what happens? If If is variable, that is what we are discussing in the last lecture, that if If is variable, what is the situation? If If is variable or it is not constant, if it is not constant, the damper currents in the d axis will not be constant. So, due to the change of the field current in the d axis, we will have a damper current in the d axis, and the damper current can be evaluated in the following way. We have the damper equation here, Vkd equal to 0, Rkd into Ikd plus P psi kd, and psi kd is the total flux linkage in the d axis damper winding, which is given as Lkd Ikd plus Lmd into If. And then when we substitute this in the previous voltage equation and we simplify this for Ikd, we do get an Ikd, because If is not constant, and hence the derivative of the field current, this one, is non-zero. So, due to the change in If, we will get a change in Ikd, and Ikd will be negative of this. So, if we increase the field current, it means we are trying to increase the flux, and by the property, the flux linkage will be kept constant, and the flux linkage will be kept constant by the damper winding current, which will induce a negative current, so as to maintain the flux constant for a time being. In the steady state condition, damper currents will die down, because it is a dissipative circuit. We have the damper inductance and the damper resistance. So, the damper current will die down at a time constant, which is equal to the damper inductance by the damper resistance. So, this is the time constant Lkd by Rkd. So, with this time constant, damper current will gradually die down. In the steady state condition, the flux will reach the final value, and the torque will also adjust to the final value. So, we will see that if this is the situation, the torque response is not instantaneous. This is our expression for the torque that we discussed in the last lecture. For the vector control drive, we have Pe is equal to 3 by 2 into P by 2, Lmd into Ia plus Ikd into Iqs, and here Ikd is non-zero, because the field current is variable. So, this is now variable. When we change the field current, we will have a damper current, and the damper current will be the negative of Lmdp into If by Rkd plus Lkdp, and this damper current will be added with the field current, and that will be responsible for the torque production with the interaction of Iqs. So, here what we are trying to do, we are trying to change the torque not by changing Iqs, by changing If. So, we will see the response here. The response will look like this. What we are trying to do here is this, that we are trying to change If. We are giving a step change in If. In this case, this is our t axis, this is origin. So, due to the change of the field current, damper current will spring up, will appear, and the damper current will be in such a direction so as to keep the flux constant for the time being. Damper current in fact will be negative of Pf. P is the derivative operator. So, if we increase the field current, damper current will be negative. If we decrease the field current, damper current will be positive. So, here we are increasing the field current, and hence the damper current here will be negative, and it will decay down to 0 as per the damper time constant. So, due to this negative damper current, the torque, which is the product of If plus Ikd and Iqs, will be delayed. because damper current is gradually decaying down and the torque will gradually increase to the steady value. So, this is the torque response. Initially it is 0, then it will take some time to reach the steady value, this is the steady state response. So, there is a delay in the torque production. So, this is T e. So, we see that when we change the field current to change the torque is delayed, and hence it is advisable to keep the field current constant. The field current change will induce a damper current and will further delay the torque response. Now, this is about the vector control synchronous motor drive. Now, we have already said that there are two conditions. One is gamma equal to 0, and gamma equal to 0 is called vector control, as we are discussing right now, and if gamma is non-zero, it is called angle control. Angle control is sometimes preferred because you know that in case of vector control drive, as we have seen in the last lecture, although the transient response is good, the torque response is very fast, the motor power factor becomes lagging. That is a disadvantage, especially for high power application, where the power converter has to supply both the active power and the reactive power if we implement vector control. It means IDS equal to 0. So, if IDS equal to 0, the motor power factor will be lagging and the converter has to supply both real power and the reactive power. And in some situation it is preferred to only supply the active power. So, if we are interested to only supply active power, we operate the machine under unity power factor condition. So, for UPF operation or unity power factor operation, we have to use angle control. This is one of the examples where angle control can be used. So, in angle control, gamma is not equal to 0. So, we will now discuss the response of the synchronous motor drive with angle control. So, we will be discussing here dynamics of synchronous motor with angle control. Which means gamma is non-zero. So, if gamma is non-zero, what happens? If gamma is non-zero, the currents will have two components, IDS and IQS. So, we can say that gamma here is non-zero, which means IDS and IQS are both non-zero. So, we can say that IDS and IQS are both present, and here we can assume that IDS is non-zero, but IDS is constant. IDS is non-zero, but IDS is kept constant, and that is equal to capital IDS, but IF is variable. And IQS is also variable. So, if we have this situation, if we see the expression for the torque, we can appreciate which all terms will be present. Now, let us see the expression for the torque once again. The torque expression is given as 3 by 2 into P by 2, then we have LMD IF plus IKD into IQS minus LMQ into IKQ IDS plus LDS minus LQS into IDS into IQS. So, if this is the torque expression, what are the terms that will be present in the torque expression? IDS is non-zero. So, we cannot neglect this term will be present because IDS is present here. IDS is also present, so this term will be present. This term, this IQS is also present here. So, LDS minus LQS is the reluctance torque, that torque will also be present. What about the field torque? IF is also present, so this term will be there, and since IF is variable, IKD will also be present and IQS is non-zero. So, all these three terms will be present. So, we can say that all terms will be present, all terms will be present. Now, this becomes little complex, because as such the equation of the torque for synchronous machine is not a simple one, because it is a doubly excited system. So, we have interaction of field winding with the stator currents, we have the interaction of the stator currents with the damper currents, and hence when all the terms are present, the equation becomes complex. So, we can understand this interaction by drawing a block diagram. Now, please understand that here damper winding current will be present whenever there is a flux change. Damper winding is basically a short circuited winding, and whenever we have a rate of change of flux linkage, that winding will be circulating a current, maybe in the d axis, maybe in the q axis. In the d axis here, we have assumed IF is variable here, IF is variable. Okay. So, if IF is variable, definitely IKD will be present. So, we can say that this leads to the result that IKD is present. And what about the q axis? In the q axis, again the damper winding will circulate a current whenever there is a rate of change of flux linkage in the q axis rotor, and that is true here because IQS is also variable. So, IQS is variable here, and that leads to the fact that IKQ is present. And we can of course find out the expression for IKD and IKQ by respectively solving the equation of the dampers in the d axis and q axis. Now, let us draw the block diagram for the torque production. We can draw the block diagram for the torque production in the following way. So, we have, let us say, the field current, and the field current is changing, and due to the change of the field current, we will have a damper current. And the damper current is given by minus LMD P by RKD plus LKDP. So, this is the field winding current IF, and this is the damper winding current IKD, which is appearing because of the change of the field winding current, and this will be leading to the first term. So, what we have here, this can be fed to a multiplier, and other variable in the multiplier is IQS, and this is again multiplied with some constant term 3 by 2 P by 2 into LMD. So, this is the first component or the first term of the torque. We can see that the torque will have three distinct terms. This is the first term, second term, and the third term. So, the first term has been shown in this particular figure. This is the first term. What about the second term? We can also find out the second term here. What is the second term? Second term is minus of LMQ IKQ into IDS. IKQ will be appearing because of the change in IQS. So, IQS change will initiate a damper winding current in the q axis. So, that we can show here, that we have this IQS, and IQS, when we change this IQS, damper winding current in the q axis will appear, and this equation can be similarly derived, similar to the equation in the d axis, we will have similar equation in the q axis. So, we can show that as minus of LMQP divided by RKQ plus LKQP, and this is IKQ, and this IKQ has to be multiplied with IDS to produce a torque. So, this is multiplied with IDS. So, we again have multiplier here. So, we can multiply this with IDS, and then there is some constant. This constant is 3 by 2 P by 2 into LMQ. This is the second term, and we have the third term, and the third term is basically the reluctance torque, which is LDS minus LQS is the constant term into IDS into IQS. So, it is the product of the two currents in the two axes, IDS into IQS. So, this term is called the reluctance torque. It is coming up because of the saliency in the rotor. When LDS is not equal to LQS, this torque appears. So, we can write down the third term here. We have IDS here. So, we can multiply that with IQS, and IQS can be obtained from this. And then what we do here is that we have the constant term is 3 by 2 P by 2 into LDS minus LQS. So, the summation of these three terms will give us the final torque. So, when we find out the final torque will have the following expression. This is negative here. So, we are discussing about the torque production in the angle control situation when IF is variable. So, IF is variable, but IDS, which is non-zero, was constant. So, we have seen actually there are three different terms in the torque, and all the three terms are present. So, the torque equation is little complex, and we can show the torque production by means of a block diagram. So, this is the block diagram that we are talking about. So, this is the first term that we have here, which is the interaction of IF plus IKD with IQS. The second term is the interaction of IKQ, because IQS is changing. So, we have a change in IKQ, the damper winding Q axis current with IDS, and the third is the interaction of IQS with IDS. This is our IDS and IQS, they are multiplied, and then we have a constant term which is 3 by 2 into P by 2 LDS minus LQS. So, the final torque expression is TE, which has got three terms. The first term is here, the second term will have a negative sign in this case, and the third term is the reluctance torque, which is LDS minus LQS 3 by 2 P by 2 into IDS into IQS. So, in angle control case, we have seen that the torque expression is not very simple, it is quite interactive, and hence the torque does not build up instantaneously. It takes some time to build up, because the interaction of the damper winding currents, and the damper winding currents spring up in the transient condition. In the steady state, they again go down to 0. So, due to the existence or presence of damper winding current, the torque is delayed. So, we will take another situation where all currents are variable, IF is variable, IDS is variable, and IQS is variable. So, that is the most general situation. So, dynamic response for angle control when IDS, IQS, IF are variable. All are variable. IDS, IQS and IF, all currents vary. So, under that situation, the torque expression, all the three terms will be present as you already seen, but it will be little more complicated because IDS is not constant. So, the damper winding D axis current is contributed not only because of change in IF, but also because of change in IDS. So, we will see by means of a block diagram how this torque is produced. Now, if we see by means of a block diagram, we will see the following. We have the field current here, IF, and then we have the D axis stator current, plus and plus. Then due to the change of these two current, we will have IKD. So, IKD will come up because these currents change, LMD P by RKD plus LKD P, and this is IKD. And this IKD is added with IF. And then what we have here is IQS. This is the first term. We have the torque constant here 3 by 2 P by 2 in LMD. So, we have the first term of the torque equation. Similarly, we have the second term as we have seen in the previous case. The second term is the interaction of IKQ with IDS. Now, how IKQ is coming to picture? Because IKQ is the Q axis damper current, and that comes into picture because of the change of IQS, the Q axis stator current. So, we have IQS, and then from because of the change of IQS, we will have IKQ minus LMQ P by RKQ plus LKQP, and this will be IKQ, and this IKQ is again multiplied with IDS. These are IDS, and this is multiplied with a constant 3 by 2 P by 2 LMQ. So, this is the second term. Now, what about the third term? Third term is the reluctance torque, which is the product of IQS with IDS into LDS minus LQS. So, we have the product of IQS and IDS. So, IDS is here, and we will have again another multiplier, and IQS obtained here, and then we have the constant, and the constant is 3 by 2 P by 2 into LDS minus LQS. So, these are the three terms of the torque. The first term, which is the interaction of IF and IKD with IQS. Second term, the interaction of IKQ with IDS. The third term, the interaction of IDS with IQS, and then we have the final expression for the torque. We have a summer here, this is plus, and then we have this is minus. The third term which is coming from this side, this is the reluctance torque, and the final torque is TE. Now, we have already seen that how complicated is the equation for the torque. Now, here this is a general situation where everything is variable, gamma is not equal to 0, which is angle control, and the torque all possible torque is present here, the field torque, the damper winding torque and the reluctance torque. So, this is a very general situation. Now, as I was talking little earlier that we have vector control, which means gamma equal to 0, the torque response is very good, and when gamma is not equal to 0, we call it to be angle control. Vector control leads to a lagging power factor, we have already seen that. And angle control, by means of angle control, we can achieve unity power factor, which is expedient for high power drive. So, we can think of a high power application of synchronous motor, where we want to operate the motor under unity power factor condition. So, we will now discuss the operation of synchronous motor drive under unity power factor condition for very high power application. So, unity power factor operation of synchronous motor. Now, before we understand this unity power factor operation, we make some simplification. For simplicity, we won't consider saliency. We assume that the motor is a cylindrical motor. So, what we have here, we have the phasor reference. So, we can draw the phasor diagram. This is our phase A reference, the stationary phase A, and the rotor is rotating at a speed of omega r. So, we have the d axis of the rotor, this is the d axis of the rotor, and the rotor is rotating at a speed of omega r, and this angle which the rotor obtains with phase A reference is angle that is theta r, is the rotor angle. And naturally we can say that the field current is along the d axis. So, if we show the field current phasor, this will be IF, and we also have armature current, and armature current will be in this direction. This is armature current, we can call this to be IA, and the resultant of the field and the armature, in the machine we have two excitation, the field excitation and the armature excitation, and the resultant of the field and the armature is the resultant current, which we call to be the magnetization current. So, this is the resultant MMF or the magnetizing current is Im prime, which is the resultant of IF vector and IA vector. Each one is a vector, because MMF is a vector. So, we can represent each current as a vector. So, this Im is a vector which is along this direction. As per the triangle, the law of triangle, we have two sides of a triangle and the third one is Im, and this armature current is so controlled that this angle is 90 degree. The angle between IA and Im prime is 90 degree. Now, there is a reason behind it. This Im prime is the magnetization current which will be producing the stator flux linkage. So, we can assume that the stator flux is along the same direction. So, we can assume that the psi s is along the same direction, we can call this to be psi s, and the vector for the armature voltage is right angle to psi s, because psi s will induce the armature voltage or the armature back EMF. If we neglect the resistance drop, the back EMF or the induced EMF and the voltage are the same. So, the induced EMF will be leading the flux by pi by 2. So, if this is our flux vector, the induced EMF vector will be pi by 2 leading the flux vector. So, this is the induced EMF vector. We can call this to be E or V, and we call this to be V because we assume that the resistance drop is negligible. So, if this is V, this angle is also 90. So, under this situation, we have a right angle triangle here, and we can write down the following expression. Now, this angle between the d axis and the stator flux psi s is also a vector. This is called the angle that is delta, the torque angle. So, we can from this right angle triangle we can say that IF is equal to Im prime by cos delta. So, if we maintain this relationship, we can achieve UPF operation or unity power factor operation. So, this Ia will also be along the voltage vector. We can say this is also Ia. This vector is Ia, this vector is also Ia. So, we see that if we have this right angle triangle condition, the voltage and the currents are in phase, and hence we can say that the power factor is unity. The angle between the V and I, theta is equal to 0 here. Theta is the power factor angle and cos of theta is 1. So, we can say that the motor is operating under unity power factor condition. We can define a few other angles here. So, this angle is called the voltage delay angle. This is delta prime. So, we can define the various angles here. The first angle in this case is delta. Delta is called the torque angle. This is the angle between the d axis and the stator flux. And then we have this delta prime, which is equal to delta plus pi by 2. We can call this to be the voltage delay angle. Voltage delay angle. This is delta plus some constant, that is pi by 2, and this is the angle by which the voltage is delayed or leading from the d axis of the rotor. And then we have theta r. Theta r is a rotor angle. This is our theta r is angle between the phase A reference and the d axis, and the motor is rotating at a speed of omega r. So, the angle that d axis obtains with phase A is called the rotor angle. And then we also define another angle called beta. Beta is equal to delta prime plus theta r. So, this angle is beta. We can say that this angle is the beta. So, we have all this angle defined in the Phasor diagram here, and to achieve this unity power factor operation, we have to have certain condition. The first condition is that the field has to be controlled as per this equation. So, this is what we have to implement. We have to ensure that the field current is controlled in accordance with this equation. This Im prime is the magnetization current. So, what we usually do, we keep the air gap flux constant. So, if we want to keep the flux constant, we keep the magnetization current constant. So, Im prime is kept constant up to the base speed. And what is the value of Im prime? Now, Im prime is approximately given in the following way. So, this Im prime is equal to the base voltage V base by omega base, the base frequency, into LMD. So, we assume that delta angle is very small. So, Im prime can be approximately the current through the d axis magnetization inductance. So, this is LMD is the d axis magnetizing inductance. So, omega b is the base frequency in radian per second. So, the base voltage per phase is equal to Im prime into omega b into LMD. So, Im prime can be approximately be equal to V base by omega b into LMD, which is kept constant for omega r less than omega b. Omega r is the electrical speed. When the electrical speed is less than the base frequency in radian per second, we can assume that this Im prime is kept constant. Im prime is constant. Now, beyond the base frequency, beyond the base speed, Im prime is changed. And how it is changed? it is changed in the following fashion. Im prime is equal to V base by omega r into LMD for omega r higher than omega base. So, when the speed increases beyond the base speed, the magnetizing current is reduced. V base is a constant quantity, base voltage is constant, that does not vary. So, if the speed increases beyond the base speed, we decrease Im prime, and that is called field weakening. And what about the voltage here? So, we can define the armature voltage in the following fashion, that is equal to a constant plus k into absolute value of omega r. We know that we have to keep the volt per hertz constant. To keep the volt per hertz constant, we change this armature voltage as a function of the frequency. When the speed increases, voltage has to be increased proportionately, and the C here, this constant quantity C here is added to account for the resistance drop. To account for resistance drop at low frequency or low speed. So, we know that we have to increase this voltage with the increase of speed, and after the base speed, we know that we have to keep the voltage constant, because when omega r is equal to omega b, the voltage reaches the rated value. So, after the base frequency, we keep the voltage constant. So, we can say that the voltage is kept constant for omega r higher than omega b. So, we can say omega r modulus, it can also be a negative speed. For omega r higher than omega b, the voltage is kept constant. So, this is actually the structure here. So, if we see the function of the voltage, so this is V A and this is our omega r. So, initially we have offset in this case, that is C, and as the frequency or as the rotor speed changes here, the voltage is increased, and then after the base speed is reached, the voltage is kept constant. So, this is the function of V A against omega r as a function of omega r, and this is basically done to keep the magnetizing current constant below the base speed. Here we can assume that Im is approximately constant, here Im is reduced. So, we can call this to be field weakening or flux weakening. And here we operate under constant stator flux. So, up to the base speed, this is basically our base speed. So, below base speed we operate under constant stator flux condition, and beyond base speed we go for flux weakening. So, this is basically the voltage profile, and the voltage is a function of the speed. As the speed increases, voltage also changes. Beyond the base speed, the voltage is maintained constant, which leads to flux weakening. So, this is basically the way we control a synchronous motor under UPF operation, under unity power factor operation. Now, what is the application of this kind of drive? This kind of drive is applied in high power application. For example, we can have a cyclo converter feeding a synchronous motor. Now, when we have a cyclo converter, the stator is fed from cyclo converter. So, we have phase A, phase B, phase C, which are fed from cyclo converter. The field is also controlled from a rectifier. So, we can see how we can have a cyclo converter fed synchronous motor drive with unity power factor operation. So, we can show in terms of a block diagram and see how we can implement this block diagram in practice. So, we have cyclo converters. So, these are the cyclo converter blocks. And the cyclo converter, each one is having two anti-parallel bridge, and we have isolation transformers here. And then we feed the armature of the synchronous machine. So, and we to have an encoder for the position feedback. So, this is our encoder. So, this has to be variable speed drive. So, we have to have a speed control, we have to have a speed feedback. So, here is our reference speed omega star, and then we compare that with the actual speed and we feed the error to a PI controller. It is a simple PI controller. Then we have a limiter to limit the output of the PI controller. PI controller usually consists of a proportional gain and an integral gain. So, output sometimes can hit infinity if not properly limited. So, we have to use a limiter following a PI controller to limit the output. And then this has to be something to do with the torque. So, the output of the limiter is the voltage delay angle delta prime, as we have already discussed. So, this voltage delay angle is this angle delta prime, angle between the d axis and the voltage vector V or VA. And here this we add with the rotor angle. We have a phase delay block. It is simple, it is a addition of delta prime with theta r, and what we obtain is beta. And this is the cyclo converter. This is the cyclo converter module that we have. And the cyclo converter has three phases. So, we have phase A, phase B and phase C, and in every phase we have two anti-parallel bridges. This is our phase A, this is phase B and this is phase C. Similarly, we have the currents here I A, here we have the currents I B, and here we have the current I C to the armature of the synchronous machine, and this current is bidirectional. It means this phase A current is a AC current. So, in AC current we mean it can be positive, it can also be negative. So, to facilitate the bidirectional current flow, we have to have two bridges connected in anti-parallel, two SCR or the thyristor bridges connected in anti-parallel. So, this is shown schematically by two thyristors in anti-parallel. So, each one is a bridge. So, per phase we have two 6 pulse bridges. So, per phase we have 12 thyristors. So, 12 here, 12 here and 12 here. We have 6 plus 6 12, 6 plus 6 for phase B and 6 plus 6 for phase C. So, in total we have 36 thyristors in the cyclo converter feeding the armature of the synchronous machine. And controlling this cyclo converter, to control the cyclo converter we need a reference voltage, and the reference voltage means we need an amplitude and a phase angle, and the phase angle is beta. What about the amplitude? The amplitude is obtained from the speed. So, we have already seen that we can have this voltage generated by means of a function generator. So, this is our V A star, and the V A star is obtained by means of a function generator from the speed signal. So, we can feed here the speed signal and we can generate V A prime, and this V A prime and beta will serve as a reference of the cycle converter. So, we have 3 phases and we can generate any one phase. Say for example, if we generate phase A, we can generate phase B and phase C. Phase B merely lags behind phase A by 120 and phase C lags behind phase B by 120. So, in fact, if we have the amplitude and angle of phase A, we can generate all 3 phase reference for the cyclo converter, and then this cyclo converter will be feeding 3 voltages to phase A, phase B, phase C of the armature. What about the field winding? Now, if we see the field winding is excited by means of a separate converter. So, this is our field winding, and we use a converter for energizing the field winding. So, we have again a 3 phase converter, and this is the field winding which is fed from the 6 pulse 3 phase converter, and we control the field winding in accordance with the equation that we have already derived. What is the equation? If prime equal to Im prime by cos delta. So, what we have here is the following. We can generate the reference current of the field winding If star, that is equal to the magnetization current Im prime by cos delta, and this becomes the reference current for the field winding. So, we have positive and negative here. This is If star, and we can have a current sensor to sense the field winding current. We have the If as a feedback here, and then this field winding current error is fed to a second PI controller, PI2, and we can have a limiter also here, and then we can generate the triggering pulses alpha to the converter bridge. So, this is how we can control the field winding current. The field winding current is controlled by means of an independent 3 phase 6 pulse converter as shown in the figure. Now, how do you obtain delta? Delta is the torque angle. So, we can obtain this delta by means of a block called torque angle estimator. So, this is basically estimation block. So, what we do here is this: we take the feedback of the currents here. We take Ia here, we take Ib. We can have the current sensors. We can sense Ia. We can also sense Ib and use as a feedback to this torque angle estimation block. And we also have the feedback of the field current If. So, from Ia, Ib and If we can calculate the torque angle, and this torque angle delta will be input to this field current reference generator block. So, If star equal to Im prime by cos delta, and delta is obtained from the torque angle estimator. So, we keep this Im constant here. We can have the Im fed here as a reference, and we can generate delta. In this case, we can calculate cos delta and we can find If star, and this theta can be obtained from the encoder. We can have another block called angle resolver. From the encoder we can calculate theta r and omega r. So, this is an example how we can use a synchronous motor drive with unity power factor condition, and this is a cycle converter fed synchronous motor drive, and the cycle converter are very robust. They can be designed for very high power application, and this kind of drive that we are discussing can be used for very high power and low speed application, for example in cement kiln, mine winder, and applications for high power and low speed, as we have already mentioned. So, in the next lecture we will try to understand how we can calculate the torque by using a torque angle estimator, and what is an angle resolver, and how can we find out the speed and the rotor angle theta r by means of an angle resolver.